Hey everyone, today we're going to continue our talk on rotating objects. So far we've talked about kinematics, our position, angular position with respect to time, our angular velocity with respect to time, and our angular acceleration with respect to time, which we compared to our translational motion. We work them basically the same, we're just using Greek letters. But in order to calculate our angular acceleration, unlike our translational acceleration where we just solved F equals ma, we summed our forces and multiplied our, or we could divide our forces by mass and we'd end up with our acceleration. It's not going to be quite as simple with our angular acceleration to solve for because our mass is going, or our mass, our rotational mass, if you will, this I in our fifth equation down, is going to depend on the shape of the object as well as its net mass, and where the axis of rotation is located of this object. So to give you a better idea of what moment of inertia is, this what I always refer to as angular mass, or like I said, moment of inertia, we need to be able to, as you could tell on this list of equations, to make these comparisons after we get out of our kinematic equations, we need to have this moment of inertia is in each of these equations, right? We have F equals ma goes to tau equals I alpha. We have, from translational, our momentum, P equals mv. We're going to now have L, which is our angular momentum, equals I omega, which is our angular velocity. Basically the same thing, mv, angular mass, angular velocity. And then we have our kinetic energy from translational motion, which was 1/2 mv squared. And we're going to see that kinetic energy for rotational energy is going to be 1/2 I omega squared. And once again, we're just replacing our mass with a moment of inertia, and we're replacing our translational velocity with angular velocity. So let's take a look at how we can calculate moment of inertia for an object. And we're going to look at an example of a disk, or a disk is also can kind of be viewed as a cylinder, because when we rotate an object with it's dependent on how far our material is from the axis of rotation. And moment of inertia is defined by this I equals the integral of r squared dm. And if you've never seen dm in an integral before, since you all only were required to have Cal 1, I doubt you have seen it. It's just the integral of the volume of an object multiplied dependent on the density of the object. So this row here with the r is saying that we have some density. It's how, the mass of an object per volume depending on our radius. Well, in here we're not going to have our density dependent on our radius. We're just going to assume that our objects are uniform density, which makes that row, our density, a constant, which we could pull out of the integral. We don't need to worry about that. Well, we don't really need to worry about it either way, because I'm not going to ask you guys to calculate this, but just to give you an idea where moment of inertia comes from. So now we have this integral that's dependent on the density, so that's just going to depend on what material our objects, our disk in this case, is made out of. And then we have the integral r squared dv. So we need to think about how to integrate to get the volume of a disk. So looking at this disk here, disk has a radius and a height is generally how it's described. And to get the surface area on the top, we just need to do pi r squared, and the height of this is multiplied by the height of this, and we'll have the volume. Or if we think about it in terms of integrals, we could do the triple integral, our constant still out in front, and then we're going to integrate over dr, d theta, dz. And this second r here is from converting from Cartesian coordinates to cylindrical coordinate system. I chose to use just because we are basically dealing with a cylinder. A disk is a thin cylinder. So solving this will become r cubed in integral, and when we integrate that, we're going to get a r to the fourth. So when we integrate, we end up getting a r to the fourth divided by 4. We're increasing our n value by 1 and dividing by it. And then we need to integrate over d theta next. So there is no dependency on d theta within the integral. So we're going to end up with just getting a 2 pi when we integrate over theta. And our coefficient out front becomes rho pi r to the fourth divided by 2. And now we just need to integrate over the height of this disk dz, which once again within the brackets, excuse me, not the brackets, within the integral there is no dependency on z, so we're going to end up with just a h, and we have rho p or rho h pi r squared times r squared over 2. And I wrote it like this because h pi r squared is the volume. And when we multiply our volume times our density, we end up with a mass. So simplifying this equation, we end up with I equals 1/2 mr squared. So we could go to our cheat sheet for a moment of inertia and compare our results to what we have offered on this table. So if we look down at F, it says a solid cylinder. I equals 1/2 mr squared. The big M is just means the total mass of the object, and then the big R showing that it's at the radius, the radius of the object. So anyways, so our disk that we integrated to over our mass density, or volume density rather, is the same. Our disk is a solid cylinder, which if you look at it, looks the same. It's just got a little more depth. But once again, it doesn't matter, moment of inertia, how the weight's distributed along the axis. It depends on how it's distributed with respect to the radius. So let's look at a GIF to demonstrate the importance of moment of inertia. If we look at these 5 objects sliding and rolling down the ramp, you notice that they all accelerate at different rates. And the cause of this is from a moment of inertia. When we have a rotating object, we have this stored energy that goes into rotating the object, where when we just have a block, the first object that's just all translational motion, all of its energy is going into kinetic energy. So we could see that a block actually will slide down a ramp, assuming it's frictionless for that block. The interface between the block and the ramp has no kinetic friction or static friction. The block should get to the bottom of the ramp first because it's putting all of its energy it's gaining from the gravitational field into moving forward. While we look at these other objects, the solid disk, the hoop, and then we have 2 spheres, and they're all arriving at the bottom of the ramp at different times. And that's all dependent on the moment of inertia. So let's look at the disk and the hoop and compare the moment of inertia of those two. So we see the solid disk makes it to the bottom of the ramp before the hoop does. So if we go back to our table and compare a hoop, which is the letter G, a thin-walled hollow cylinder, and we have our disk, which is letter F, or a solid cylinder, we see that the moment of inertia for a solid cylinder is 1/2 mr squared, but for a thin-walled hollow cylinder, it's mr squared. So a thin-walled hollow cylinder has a larger moment of inertia because we don't have that coefficient of 1/2. So more of its energy is going to be stored in rotation because all of its mass is out at its radius. So looking back at this video, we could see that the smaller the moment of inertia is, the quicker the object will get to the bottom of the ramp. And this is assuming that it has the same radius and the same mass. And so what's the deal with these two spheres? We got the orange one that makes it to the bottom first, and then we have this green one that follows up. So looking back at our moment of inertia table, we could see that our solid sphere has a smaller ratio coefficient than our thin-walled hollow sphere. So therefore, our moment of inertia for a solid sphere is smaller than a thin-walled hollow sphere, which kind of follows the same logic as when we looked at the solid cylinder and the thin-walled cylinder. So when we look at this video, we should be able to pick out which of these objects is going to, or which one of the spheres, even though we can't see it, is going to be a hollow sphere, which is going to be the one that is slower, the one that makes it after the solid sphere because it's got a greater moment of inertia. So in this case, our green sphere is a thin-walled hollow sphere, and our orange sphere is a solid sphere. Okay, so that's all I'm going to talk about for this video. I'll be sending another video out shortly where we're going to go through our torque, our tau equals I alpha, our angular, which is torque, yeah. And then we have our angular momentum, and then we'll talk about angular kinetic energy in the next coming up videos.